All right, everybody, we're looking at 7.2, forces angled third law. Guys, remember, third law, third law, third law. Here we go. Number one, they run at each other. How's the force compare? Well, Newton's law states that if two objects are exerting a force on each other, that they will apply the same force to each other, and they have to be the same. So whatever force this guy feels, this guy feels. If I call this object 1, this object 2, force on 1 by 2, this is the force on 2 by 1, they have to be the same. So how does their force compare? Same. Let's look at number 2. Same speed, but let's talk about acceleration. If it's the same force, but now we got to talk acceleration. So in this one, if the forces are equal, but this is MA equals MA, but the problem is the football player has a big mass, and this guy has a small mass. That means this guy has a big acceleration, this guy has a small acceleration. That's why it looks different, right? The little guy has a huge acceleration. All right, number 3. Which person experienced a larger average force? Okay, it's the same. All right, small insect smashes into a car. Same. Experiencing a large acceleration. The bug, though, people. All right, make sure that you explain the answer for each of these questions. Oh, do you have to do that? I don't know if you have to do that in there. Now we get to number 5. Well, again, number 5 is we have boy pushes lawnmower. Good job, boy. So boy pushes lawnmower. So he pushes it into the ground. 22 degrees with the horizontal. The boy pushes with a force of 140. Okay, so if I take the kid's force of 140 newtons at 22 degrees, I can break it up into its components. So this is the force in the x direction, and this is the force in the y direction. Force in the x direction will be 140 cos 22, and you'll get a value. And then force in the y direction be 140 sine of 22. All right, now we're looking at number 6. All right, number 6 here. All right, here we go, number 6. So what we got is we have an interesting problem. So I have a girl pulling a sled of 8.4. They're 13 meters apart. So right off the bat, you should be going, ooh, that distance is going to get interesting here. She pulls the sled with 5.8 newtons, which means she gets pulled with 5.8 newtons back by the sled. Okay, that rope, third law of force parity. So if I do F net equals MA, the F net for her is going to be 5.8. I can solve for her acceleration. F net equals MA. I could solve for the sled's acceleration. F net's 5.8. So I'm going to get these accelerations. I want to make sure they're correct, so we are actually using the correct things later. So 5, I know the battery's low. 5.8 divided by 36 is 0.161. And the next one, 5.8 divided by 8.4 is 0.690 meters per second squared. So right off the bat, that's as far as you get. It's actually a really good start, okay? But now it gets interesting because it says, where do they meet? So later in the course, we'll talk about center of mass, and we'll have a quick little way to do this. But I think it's also good to see another strategy to do this. So here's the key to this. This person on the left, this person on the right, this person's going to go here to X. This person over here is going to travel 13 minus X, okay? And I think about strategies of problem solving. I'm going to set the times. Those times are going to be the same as each other. So we're going to use that to our advantage. Now here's where it gets interesting. V final, acceleration, displacement, and time. Initial velocity for this guy is 0, but we're going to go over here. We're going to write this person out too. This is where it gets a little bit tricky. If you can think of a more simplified way, let me know. This is my 3rd time doing this problem. It's the first time you've seen me record it, though. So this guy's acceleration, we're going to say is positive 0.16, because we're going to say to the right is positive, and we're going to say to the left is negative. So that is actually very important. The displacements that the girl's going to go is positive x. Positive x. Now, if we were to, where is my pen? If we were to solve this out, I got delta x equals 1/2 at squared, my last equation. I end up with x equals 1/2 a 0.16 t squared. Okay. If I solve for t, I get 2x over 0.16 all square rooted because that square is there. Okay. So now we're going to the right side. This is where it gets a little bit interesting. This person is going to be accelerating to the left. So their acceleration is negative 0.690. That is where we're going to run into some problems here. The displacement of that right side object is going to be negative 13 minus x. They're going to travel 13 minus x, but since they're going to the left, their displacement is negative. Okay. Time? Oh, we know what the time is. Well, kind of, right? We're going to see how that works out right now. So I have delta x equals 1/2 at squared. I'm going to change color just so you can see where this final process goes. So the delta x for this last one is negative quantity 13 minus x, 1/2 a, negative 0.690, time squared. The time is down here. So we have the square root of 2x over 0.161. Okay. Now when I square that, see what's going to happen? Negative 13 plus x equals 1/2 of negative 0.690 times 2x over 0.161. I'm going to deal with all the numbers on the right side at once because it's just a mess. So 0.5 times 0.5. I know I'm low on battery. Stop telling me. 0.690 times 2 divided by 0.161. I get 4.28. So on the right side, I get negative 4.286x. On the left side, I get negative 13 plus x. So negative 13 equals negative 5.286x. I subtracted an x to the right side. Divide that out, I get x equals 13 divided by 5.286, 2.45. 2.46 meters. Again, that's one way to do it. Later in the course, we're going to deal with center of mass. This one, easiest way to do it is say, hey, I got a kid and a sled. Where's the center of mass? That's where they end up because when they pull towards each other, there's no outside forces. So we have another way to do it. How far from the girl's initial position do they meet? 2.46 meters. To me, it's number 6, part C is a pretty tough little problem. All right. You're going to see real quick, these are not as bad, the rest of these. So 6C, though, that was a tough one. So we've got 7. Robert pulls at 45 degrees. With what force does he have to pull? Well, if there's 1,000 newtons going down here, okay, that pulley redirects it. How hard does he have to pull? 1,000 newtons. Okay, number 8. We don't have to break it into components. That's it, 1,000 newtons. Diagram below shows a block. This is where we get good here. Here we go. Pen me. Diagram below shows a block on a horizontal surface. Where is my pen? There it is, guys. This is number 8. You've got a block. Pull it. Diagram shows a frictionless surface. 100 Newton force is pulled at an angle. Well, when we pull at an angle, is it okay to say we're going to have to break it up into its parts? Yes, the answer is yes. So we're going to break that up into its parts, horizontal and vertical. This is 100 cosine of 30. This is 100 sine of 30. 100 sine of 30 is going to be 50. 100 cos is, let's get that actually right. Cos of 30. Make sure I'm in the right mode. I'm not. 86.6. So horizontally, I have 86.6. What is the magnitude of the force if it establishes equilibrium? Equilibrium means it goes constant speed or not moving. Well, if there's 86.6 going forward, well, how much force do they have to be pulling backwards? 86.6. That is what number 8 is. 9. All right, number 9. Here we go. Number 9, 42 kilogram stoplights. So right off the bat, number 9, 42 kilogram stoplight. To find its weight, we do M times G. 42 times 9.81. We are dealing with Webassign. So 42 times 9.81, I get 412. So I got 412 is the weight force down. So what's the weight? Part A, done. Part B, what are the sum in the x direction? Sum the forces in the x direction to find an expression for T2. So let's do this guy. So we've got, let's look at that. So here's T1, here's T2. Now this is 33 degrees, so that's going to be 33, and that's 78, so that's going to be 78. Okay. Oh, I was hoping those are going to be complements. So sum the forces in the x direction to find an expression for T2. So T2 here will be T2 cosine of 33 degrees, T1 cosine 78 degrees. Now, since those are the only two horizontal forces, they have to be equal. So if I solve that for T2, I get T1 cosine 78 degrees all over cosine of 33 degrees. Now, if you stick that in a calculator, cos 78 divided by cos 33, I get 0.2478. So T1 times 0.248 equals T2. So the idea is, if you just divide those cosines, you'll know how they differ to each other. Okay? Sum the forces in the y direction. Okay, sum the forces in the y direction. Substitute your answer part B to find tension T1. Sum the forces in the y direction. So here we go. So we're going to come back to this. So actually, I'm going to make this big. So we need to find the vertical components. Let me get my face out of here. Sorry, kids. And so vertical, I'm going to change color for vertical. My vertical is going to be blue. Okay, song stuck in my head right now. T2 sine of 33. And this one here is T1 sine of 78. So here's the idea. Where's my pen? There it is. This guy plus this guy upwards equal to the weight force downwards. Because the weight's the only thing pulling down. So those two upwards are canceling it out. So T1 sine of 78 plus T2 sine of 33 equals 412. Okay? Going back to the problem, I want to just focus on what's it want. Sum the forces. So we want to solve for T1. So we want to solve for T1. So what do I have to get rid of? T2. So look at this. T2 equals that. So T1 sine of 78 plus T2. What's T2 equal to? It's T1 times 0.248. Sine of 33 equals 412. Okay, I'm just going to get some numbers. So sine of 78, 0.978. So T1 times 0.978 plus, I'm going to combine all this stuff. So 0.248 times sine 33. Okay, so all I'm doing is just combining this and this to get T1 times 0.135. Okay, now notice I have T1 times a number plus T1 times a number. So I can combine those T1s. 0.978 plus 0.135. So T1 times 1.113 equals 412. So T1 equals 412 over 1.113. 412 divided by that, you get 370. So T1 equals 370 newtons. There you go, 370. It's part C. Plug your answer for T1 to find T2. Oh, no, Schmear, more stuff. Stand up, let's go purple. Go Dogs. I might be trolling some of you Oregon Duck fans just because you won the Pac-12. So T2 we're going to use this equation. T2 equals 0.248 times T1. Well, if T1 is 370, I can solve for T2. So 370 times 0.248, I get 91.8. There it is. That's a tricky one. Whenever you're given the weight and you got to break it into its parts, those are by far the hardest ones. 10 though, not bad. Okay, so let's tackle 10s. 10, we got a barge. It's towed by two mules or mules. They're both pulling at 2,250. What is the net force of the barge if the friction force that must be overcome is 1,100 newtons? I don't know. So we got this force pulling at an angle. Anytime you got forces at an angle, find out what its components are. This component horizontally is the cosine of 35 degrees times the overall. So 2250 times cosine of 35, 1843. Okay. Well, look at this. This guy here, he's got 1843 going forward. The bottom mule. Okay. So look at this. We got these two going forward. But how big was the friction? 1,000 newtons. Ooh. I don't know, I'm just staring at it. So watch, I got 1843. I got two of those going forward. I got 1,000 going backwards. So what's my F net? My F net is 2686 newtons. Okay. Part B, assuming the same force of friction, imagine now that the barge is moving at constant speed. Ooh, what's the net force? Guys, if you're going constant speed, your acceleration is 0. So what's your net force? 0. Cool. If that's wrong, let me know. I think that's right. I can't even plug in answers on my end as a teacher. So I just have to guess I'm right. Okay. Find the tension in each cable supporting a 620 Newton cat burglar. What's up, cat? Ready? So, shung, shung. That's 37 degrees. So that's 37 degrees. Okay. Cat burglar. Funny. 620 newtons going down. So this is T2 and this is T1. So break it up into its components. Okay. Anytime you have something at an angle, break it up into its parts. If 620 is going down, 620 is going up. This guy's going left. This guy's going right. Okay. So I have a little triangle here. So face out of there. So we've got this triangle. X, and I'm going to call that T1. Let's solve for X first. All right, so I go tangent opposite over adjacent of 37 equals 620 over X. So X equals 620 over tangent of 37. Just get a number. 620 divided by tan 37. 823. Oh, so that's X. Well, if that's X right here, 823, that means this is 823. Now, the last step is how am I going to find T2? Easiest way, once you have two of them, I always just do a squared plus b squared equals c squared. Solve for this guy, not T2, but T1. That's it. All right, number 12. Number 12, we got ourselves a block is at rest. Okay, what is the tension? Well, this block has mg sine of theta going down the ramp. M, 34. G is 9.8. Sine of 35 degrees. We're just going to plug in a calculator. We're just going to get a number. That's all we're doing. We get 191. 191 newtons going down the ramp. So how much do you have to pull up the ramp to keep it there? 191. If it's not moving, they have to be equal. If it's sliding at a constant speed, it still has to be equal. Okay. Block is projected up a ramp. This is number 13. Big 1-3. Okay, number 13 here. Block is projected up a frictionless incline ramp with initial speed. How far up the ramp does it go? I don't know. How long does it take? I don't know. What's the speed when it gets back to the bottom? Same speed. Okay, part C is the easy one. If it goes up and down and there's no friction, it'll have the same speed at the bottom. Part C is done. Part A, don't know. So we're going to do VF, VA, delta X, and T. It wants to know how far. Okay. Initial speed, they give it to me in this problem. Now, how high does it go? That means at the top it's going to be going 0. I need acceleration. Schmear. Okay. What's the force pulling it down the ramp? mg sine of theta. That's what's pulling it down the ramp. Okay. Well, if there's no friction, if I do F net equals ma. So ma equals F net, mg sine of theta. So if I cancel out the m's, I get g sine of theta. So 9.8 sine of angle is 32.5. That's a really nice one. All right, and so I get 9.8 times sine of 32.5. I get an acceleration of 5.26. 5.26 is my acceleration. Well, look, now I can go old school. No time. What's the equation with no time? All right, so final initial squared plus 2 times a times x. Solve for x. You get a value. How you solve for time? Go back to your simple equation. V final equals V initial minus 5.26 times t. Just because the acceleration is down the ramp, you call it positive. There you go. It's 13, 14. Ball rolls down a ramp. Oof, rolling. Shouldn't have said rolling. Okay. Ignore friction. Ignore rolling effects. We'll talk about rolling later. So whenever you go down a ramp, it's just what we did. mg sine of theta. This is number 14. But in case you skip 13, I got you here. Equals ma. So the idea is F net equals ma. But if the only thing down the ramp is mg sine of theta, that is your F net. M's cancel. So g sine theta equals acceleration. If it is 19 degrees, it's 9.8 sine of 19 degrees. That's my acceleration. The ramp's 3 meters long. How much time does it take to reach the bottom? V initial, V final, acceleration, displacement, and time. V initial is 0. Acceleration is whatever that is. I don't feel like reaching for my calculator. I want to know, 3 meters, how much time? No, V final, it's my last equation. Delta x equals 1/2 at squared. Plug it in, solve for time. All right, next up, 15. Big dump truck. Ooh. Got a dump truck. It's on an incline. Oh my gosh, where's my pen? Okay, and so it sounded way too much like Tom from Parks and Rec. Sorry, guys. 15, we've got a 9-degree angle. We got mg sine of theta going down the ramp. We're going to need to solve for that because it's saying truck's mass. All right, let's solve for it. 11500. G is 9.8, sine of 9 degrees. I'm just going to get a number so we can kind of leave having to read all that stuff. Sine of 9. 17,630. 17,630 newtons. That's the force down the ramp. It says, what will it take to keep it from rolling down the ramp? I would need to have a force of friction that is identical. If I don't have the same amount of friction, it's going to speed up. Okay, so that's issue 1. What if the question said, what if it was going constant speed? Still need that much friction. That's how much friction I need to keep it from rolling down the ramp. All right, guys, thanks for tuning in. This was a tough one. Stick with it.